In this video, we're going to look a little bit further at the Biot-Savart law, specifically for a long straight wire to derive in the complicated way by integrating from 0 to infinity and 0 to negative infinity and adding up those effects. Very annoying. And then we're going to look at Ampere's law, which allows you to do this with an incredibly nice symmetric set of current, and it's much more like using Gauss's law. So that's kind of our goal for this video. This is on page 9 in your packet 11, so you can follow along. This, again, will be much easier to do with Ampere's law, but we're going to start by doing the Biot-Savart method, right? We have to do what we always do. We've got a long current carrying wire where some position P, a distance capital R from it, and for any little dl, little bit of the wire, you're a distance lowercase r with an angle of theta. And of course, as you go further and further, little r will grow bigger and theta will become more and more obtuse. And so we have to integrate all the little bits of dB to find the total magnetic field. What is the direction of this? Well, for that, you're going to use your right-hand rule, right? The B field should be coming out of the page at you at point P. And so every little bit of IDL will give you a magnetic field out of the page, less and less as you get further away from it. We're going to be doing this integral. We have to include this sine of theta term because we're really interested right in that distance there, which is a little bit annoying because that sine of theta actually depends on where you are with x, where you are with r. And so we're going to need to do a little bit more work. We're going to pull out everything that's a constant. In this case, that's the 2 times mu naught over 4 pi. The reason the 2 is there, we're going to integrate from 0 to infinity and then double it instead of integrating from negative infinity to positive infinity, just for simplicity's sake. If we put all that together, we are really worried about this dx, a little bit of distance times sine theta over r squared. And we need to figure out what's going to happen there. When it comes to the sine of theta, well, the sine of theta is capital R over little r. Capital R is a constant, which is nice. So we can deal with that. And we end up with an R cubed, right, down there. As it turns out, R cubed needs to be written in terms of x. We've actually seen this before when we did this kind of work with a long line of charge. When we were doing the electric field, we ended up with this 3/2 x squared plus r squared thing. And we have that again. We can do the integral. We evaluate it from 0 to infinity, and we get mu naught I over 2 pi r. The big deal about this is that we have something that just depends on r, how far you are from the wire. It's a 1 over r relationship, which hopefully makes sense because it's sort of this cylindrical symmetry. Anywhere you are a certain distance from a long straight wire is going to be in a circle, and that allows us to come up with this relationship. Now, that is, of course, the Biot-Savart method. But we want to see that we get the same result using Ampere's law, which is much simpler and allows us to use kind of the shortcuts and tricks we learned from Gauss's law in electric field. So how do we do this? Well, when we're talking about Biot-Savart, we're always talking about this relatively complicated thing here that includes a cross product. We have to integrate all these little pieces of dB. And oftentimes we also have to deal with the fact that because it's a vector, we need to eliminate, maybe x or y component of that when we integrate it and turn it into just a scalar. Ampere's law, on the other hand, has this kind of closed integral of b dot dl equal to mu naught times I enclosed. So just like we enclosed charge with a Gaussian surface, with Ampere's law, we're going to enclose current with something we call an Amperian loop. So this dot product is integrated around the Amperian loop instead of being integrated over a Gaussian surface like it is in Gauss's law. So an Amperian loop is any closed loop, just like a Gaussian surface was any, three-dimensional surface. But just like Gauss's law, there are smart loops to use and not so smart loops, right? A circle, very simple. Even a square or a rectangle, any polygon that we can figure out kind of what's going on and easily talk about the different surfaces is usually a good loop to use. Something kind of irregular, although technically acceptable, is very hard to do the calculation for. So we can start by thinking about this loop, ABCD. This is a rectangle, right? And we have L is the length along each of those sides of it, and the magnetic field is going to the right in this picture. So if we want to do B dot dl here, we can think about each of the segments. Well, L is along the Amperian loop, so it's with the B field from A to B. It's 0 because they're perpendicular to each other, B dot dl for the next segment. Then we've got negative BL from C to D, and we've got 0 from D to A. If we put all that together, we end up with 0 for our integral, our closed integral here. And this leads us to the question, how do I get a non-zero, this is that sort of flux kind of term, integral of B dot dl? Well, the only way to do that is for us to enclose some current. If there is current going through the loop, then you can actually get something that is non-zero there. And the analogy with Gauss's laws, right? If you enclose zero charge, you just put a Gaussian surface in a uniform electric field, you get no flux. In this case, if you're talking about the magnetic field, right, if it goes in and out, you also get no magnetic flux. So we need to enclose some charge. And what does that look like? The important ideas in all of this is that Ampere's law and Biot-Savart both include a dl term, but they are not the same thing. The dl in the Biot-Savart law is moving along the current carrying wire. It's IDL, right? It's basically a way of saying which going along the current. With Ampere's law, this dl is for going around the Amperian loop. Okay, so that's the big difference. So what we're going to do is very similar to what we do with Gauss's law. We're going to visualize and sketch the magnetic field. We'll pick and draw an Amperian loop that meets the criteria, namely that the point we care about is on it, and that the B field is either 0 or nicely perpendicular to the loop at all points, parallel or perpendicular, and then we're going to state and apply Ampere's law by doing that integration. So here's a simple one. We have a long current carrying wire. It's coming out of the screen at you, which means you would have a counterclockwise rotating magnetic field, right? So we can draw that. We know that we need to find its direction at P, which is going to be just up from the right-hand rule. And if we draw our Amperian loop, it should be centered around the wire, enclosing the wire, and it should go through point P. This is the only point we care about on the loop, is on the loop, and the loop encloses the current. Those are the key things. Now that we've done that, we can apply Ampere's law. Mu naught I enclosed, that's pretty easy. The I enclosed is just the I that we're given in this problem. Mu naught is a constant. B should be the same everywhere, and dl, the integral all the way around the circle, is just the circumference of the circle, 2 pi r. If we rearrange that, the magnetic field is mu naught I over 2 pi r, which is exactly the same we got when doing the more complicated Biot-Savart integration. So much easier, and that's great for a kind of highly symmetric arrangement of charge. So now that we've done a single line of charge, of current rather, we can go ahead and do something a little more complicated. What if we have a magnetic field and we have a wire that's not so small that we can just ignore its thickness? We actually want to know what's going on inside of it and outside of it. So in order to do that, we look at the end, right? We basically have current coming towards us, right, along it. And so we want to think about the magnetic field. Inside, it's clockwise. Outside, it's also clockwise because, the magnetic field from the current coming out will do that and add up. We can draw an Amperian loop. There's lots of loops we can draw, but if we're thinking about inside of this current carrying wire, it should be a distance r from the center that encloses some current, but is not outside of the wire. Now we can state and apply Ampere's law. In order to do that, we need to think a little bit about what's going on. The area enclosed divided by the area total, cross-sectional area, is how much of the current we get. So that's a way of thinking about this. Then we have I mu naught. That tells us how much current is enclosed. We still have the same B times 2 pi r. We've made the magnetic flux side of the equation very simple. We get mu naught I over 2 pi r, all of those things again. But then we have this factor of pi r squared over pi r squared, where the r in the numerator is the Amperian loop's radius, and r in the denominator is the total radius of my wire. A lot of things sort of cancel out and recombine. We end up with mu naught I over 2 pi capital R squared for the whole wire times little r, which hopefully reminds you of when you looked at the electric field inside of a charged up object. It was a direct relationship. At the center, you had 0. At the outside edge of the thing, you had your maximum. And that's exactly what we see here happening, which hopefully, makes this at least a little bit comfortable, even though it's a different kind of problem. Once you're outside, right, you get a different result. But when you're inside, B increases linearly inside the wire. For this particular case, we get 0.4 Tesla per meter times the radius. And that means we would have a graph that looks something like this: 0 magnetic field at the center, up to a maximum value when you get out to the radius. And then when you go outside, we have a 1 over r relationship, because at that point you're enclosing all of the current. It's just the answer to the previous example. The other examples we want to think about are a device called a solenoid. Solenoids are very helpful. If you put a piece of metal in there, you've created an electromagnet. These are used for lots of useful things. It multiplies the effect of the magnetic field from a coil of wire, because you keep doing them over and over again. And in this visual, you see that outside it's a very weak magnetic field, but inside it's strong. And we would expect still for the magnetic field to depend on current, but it might also depend on how long the solenoid is, how many coils of wire there are, those kinds of things. And so we end up describing this in terms of this value n, that is the number of loops per meter in the solenoid. Because the more densely wound it is, the more loops per meter, the more magnetic field effect you get. And so inside, you have essentially a constant magnetic field, and outside, you have essentially 0 magnetic field. So this is what it looks like inside. Notice I've done a cross section here. The magnetic field is all going to the left on the screen, and we've got current going in at the top and out at the bottom. We can draw an Amperian loop here to include some of the current, and this one looks a little bit different because we're just containing some of those wires. Here I'm using a rectangle, and when we apply Ampere's law, the outside part of the loop doesn't do anything. The 2 vertical sides of the loop don't do anything. And only the inside matters, because it's the only one interacting with the magnetic field, the AB segment. So we get B times L, whatever length that is, calling it L, and the other 3 sides have 0 effect. So we have the current enclosed, is going to be the current for the wire times how many loops of wire there are, right? Current times the length times the number per meter, which ends up just being the number that you've enclosed. And we end up with the magnetic field inside of a solenoid is mu naught times the current, mu naught again, multiplied by n, the number of coils per meter. The more coils per meter, the stronger the magnetic field. The more current, the stronger the magnetic field. And so magnetic field is a constant inside and depends on those 2 variables. The other shape we want to look at is something called a toroid or a torus. It's basically a donut or a bagel. We've got wire wrapped around and around and around, and inside could either be a gap with nothing in it, or you could put metal in there to make a stronger magnet. But B is totally enclosed and circles around inside the toroid. So when we think of it, if we were to slice it, like slicing a bagel in half, you've got out of the page and into the page current coils, and we're interested in the magnetic field inside of that loop. Will it be uniform? Will it be different? Well, we know that the magnetic field circles inside there. Will it be uniform? No, because the further out you get, right, you're getting further away from the enclosed current, because only the little X's, the into the page currents, are going to show up there. And so how do we draw our Amperian loop? Well, we draw our Amperian loop that encloses all of the inner coil of wire, all of that current, but doesn't include the whole thing. Because if it did, outside, of course, you've got into and out of the page matched pairs, so you would always have 0 current enclosed. So if we apply Ampere's law, mu naught times I, once again, we have B dot dl, which is just going to be B times 2 pi r, because it's just the circumference of a circle. All n turns are enclosed. So we can basically take I multiplied by how many coils of wire make it up, and we end up with mu naught I, number of coils, divided by 2 pi, a bunch of constants, times 1 over r. So it's not a constant magnetic field, and it goes like 1 over r as you go from the inside to the outside of that toroid. And it's stronger closer in, which hopefully makes some sense. The last thing I want to do is look at a finite, an infinite plane of current. Now, this one's a little hard to visualize, but if you had just a ton of wires next to each other with current all going in one direction, that's what we're dealing with here. We have the magnetic field from each of them that would kind of add up and add up and add up. But in effect, what happens is that the magnetic field along the top of it, especially if this plane is infinite, just goes in one direction. Okay, and we add up all those effects, and the up and down effects go away, and you end up with a magnetic field all in one direction. Below, you get the same thing, so it's one way above and one way below, to the left and to the right. That's what the magnetic field looks like. So once we have that, we can start to think about an Amperian loop. Again, in this case, I'm going to pick a rectangle because 2 sides will be perpendicular to the magnetic field, so we'll get nothing from our integration. And then 2 of them are with the magnetic field. So we apply Ampere's law. In this case, we call that length L. If we integrate around the loop, notice that I have 2 positive BLs this time, because the direction as I go around the loop, if I start from A, go A, B, C, D, I'm always going with the magnetic field, and I get twice B times L. I have 2B times L, mu naught times I enclosed. In this case, because of the way, this current density is listed, a lambda, current per meter, you can write current lambda times the length of the wire or of the loop, and you get mu naught lambda over 2, which is a constant, which is pretty interesting, right? You get a constant magnetic field from an infinite plane of current, which should probably not be that surprising. That's what happens when you have an infinite plane of charge as well, and we found that using Gauss's law. All right, that's it. From Ampere's law. We'll do some practice problems with this and think about how we model the magnetic field as we go.